Muscles, force and body movement. Static motion. By Assistant Professor of Medical Physics, Dr. Maad Al-Arif. Force and motion. Force, F, is defined as any effort applied to translate or rotate an object. Force developed between two or more objects, which can be of two types. 1. Contact forces, which needs a physical contact between the objects to be developed. Example, pushing a car or kicking a football. 2. Field forces, no need for physical contact between objects. It can develop between objects through space. Example, Coulomb forces, gravity forces, magnetic forces and nuclear forces. Force is measured in unit of Newton, N, where 1 Newton equals kg m per second square. Torque, Ta, is the ability of the force to rotate an object around an axis. Torque is a vector quantity, it means must have a magnitude and direction. Direction of torque can be either positive or negative, depends on the direction of rotation of the object. The objector is regarded as lever. Positive torque, when lever rotating counterclockwise. Negative torque, when lever rotating clockwise. The magnitude of the torque is given by the following equation. Torque is measured in unit of Newton multiplied by m.
Body motion is controlled by muscle forces, initiated by contraction or extension of muscles. Skeletal muscles control the movements of the body limbs. When more than two forces acts on the limbs, limb assumed as a lever, at the same time, the lever is either rotates or stay without motion at equilibrium. If the vector sum of the torques generated from all forces is 0, then the levers stay at equilibrium, stationary, and then we can say that the vector sum of torques is 0, as in the equation. If the vector sum of the torques is not 0, then the lever must rotates with a net torque either positive or negative according to the direction of rotation of the lever, and we can represent this in the following equation.
The law of levers. Archimedes is the first who puts the law of levers. He find that the ratio of load, W, to the forces, F, applied is equal to the ratio of their arms and is given by the following equation. In the above equation, W is the load, F is the force, D1 and D2 are the arms of the load and the force respectively. Positive torque, when lever rotation is counterclockwise. Negative torque, when lever rotation is clockwise. Classes of lever. The below figure shows the three classes of lever systems. Looking to the figure carefully, we can say that the difference between them is the position of the force, F, and load, W, with respect to the axis of rotation. Levers in the body. 3 examples for lever systems in the body are shown in the figure, in which the W is the load, F or M is the muscle's force needed to support the pivot point, the axis or rotation. In solving problems regarding the levers in the body, we must convert the anatomical structure of the body to a force-body diagram below each, as in the figure. In the force-body diagram, we regard the part of the body as a lever and show only the forces acting upon it. Example 1, the forearm is lever. As you can see in the figure, the biceps muscle pulls the arm upwards by muscle force M. The opposing force is the weight of the arm H positioned at the center of gravity of the arm, CG. No other load is found. When the arm become at balance, then the sum of all torques must be 0. We can follow the equations in which the two torques are available. One torque due to the load of the hand. The second is due to the muscle force. All forces applied are perpendicular to the lever arm with approximate value of H is about 15 N. Therefore, by calculation we find that the muscle force needed is M equals 52.5 N. Now if the arm is lifting a weight W, the biceps muscle can be strengthened and apply more force to be compensated the increased torque by the load W in order to be at balance again. Since we have a balance, the sum of all torques must be 0. Again, we can construct the lever's equation by adding the torque due to the weight W. Solving the equation with respect to muscle force needed, we can find that muscle force increase linearly with the load in the hand. Example 2, the whole arm is a lever. As in the figure now, the deltoid muscle pulls the whole arm upwards by contraction with a tension force F or T at a fixed angle alpha with respect to the arm. The opposing force is the weight of the arm H at its center of gravity, CG, and the possible weight W hold in the hand. Look the force-body diagram, please. When the arm is at balance, then the sum of all torques is 0, which is equal to the vector sum of the torque from the muscle force and the torque from the weight of the hand and the torque from the weight W. By substitution and construction the equation, we found that the tension in the muscles is about 1,280 newtons. The mechanical advantage, MA, refers to the ratio of the force, F, to the load, W. Accordingly it is given by the following equation. Mechanical advantage also refers to the amount of force needed to lift certain load. If mechanical advantage is greater than 1.0, little force is needed to lift the load. If mechanical advantage is 1.0, the force needed is equal to the load. If mechanical advantage is less than 1.0, more force is needed to lift the load. Note: less mechanical advantage is more recommended. As in the figure, the mechanical advantage of a Class 1 lever can be greater or smaller than 1.0. The mechanical advantage of a Class 2 lever is greater than 1.0. The mechanical advantage of a Class 3 lever is smaller than 1.0. Transitional equilibrium force is the reason for acceleration, translation and rotation. The object can be in transitional equilibrium if the net force acting upon it is zero. Therefore we can write the vector sum of all forces as zero. We can rewrite the same equation in 3 dimension as follows. Rotational equilibrium force can produce torque and rotation of the body around certain axis. The object is said to be at rotational equilibrium if the net torque acting upon it is zero. Therefore we can write the vector sum of all torques as zero as in the following equations. Total equilibrium for the body only happen when both transitional and rotational equilibrium available. We have 2 problems to be solved by you. Please check your final result with the answer given in each of them. Good luck.